Hello, welcome to another episode of the CNA's Opus. My name is Rich, I'm a certified nursing assistant. And what I really want to do today is I want to go back to the cell cycle and some things that are essential to the cell cycle, which are often sometimes kind of overlooked. And one of those is cyclin dependent kinases. So, and there's several different ones of them. So here, if you want to look at my lopsided circle, kind of representing the cell cycle, this is interphase up here. The interphase, the cell is basically kind of just making proteins that are necessary for its function, and it's not making proteins that are essential for its growth and replication. Now in G1 phase right here, it starts to make these preparatory these prep proteins that are going to be necessary for uh, DNA replication. It's like these pre-proteins that are making for DNA replication. Um, so down here in G1 phase, I drew this linear line of DNA. Uh, it's in the helix, but I drew it linearly so you could see it. And these are these pre-replication complexes. So in DNA, you have these origins of replication. And these origins of replication is where DNA polymerase will bind to and start copying the DNA off the template strand. So in G1 phase, it makes these origins of replication. They're just not ready yet. They're prepped. They're just not ready yet. So that's what's going on in G1 phase as far as that goes. But here in G1 phase, this cyclin-dependent kinase 4, which I abbreviate to CDK4, will bind to D-cyclin. Right? That's what it wants to do in order to bind to something called the retinoblastoma protein right here. And that will push the cell cycle forward. Also, in G1 phase, you have cyclin-dependent kinase 2, which is also in G1 phase, and that binds to cyclin E or E-cyclin. The difference is right here you have this G1S checkpoint, and at that checkpoint there's these DNA error correcting scheme where it'll check for errors in the DNA at this checkpoint, because you don't want your DNA replicating DNA that has a bunch of errors in it. So it has this pause, this checkpoint right there to check for errors. And then when it checks for errors, when it checks for errors, it'll try to correct the errors. And a good example is ataxia telangiectasia mutated, which is part of the p53 pathway, which just kind of looks for errors along the way at that checkpoint, just a pause, so that you don't replicate DNA that's mutated, because that would lead to cancer or various other kind of conditions that you don't want in mutated genes. So it has that checkpoint right there. And in order for the cell to get past that checkpoint, one of the things that it needs to do is this cyclin-dependent kinase 4 is rising steadily. But this cyclin E, cyclin-dependent kinase 2, spikes right there at the G1S checkpoint. And when it spikes, what it does is it will knock out or cause a loss of function in a tumor suppressant protein called P27. So anytime that you see that little P that stands for tumor suppressant protein. This P27 is there, and it's blocking cyclin D or D-cyclin from binding to cyclin-dependent kinase 4. It's blocking right here. So this can't do its job. And then also it's blocking right here. So D-cyclin can't bind to cyclin-dependent kinase 4, so that it can't phosphorylate the retinoblastoma protein right down here and push the cell cycle forward. So it's kind of blocking this right here. So first thing that cyclin dependent kinase 2 does is it knocks out this P27. So it makes more cyclin dependent kinase 4 D-cyclin available, and makes it more available so that it could phosphorylate the retinoblastoma protein right down here to push the cell cycle forward, right? But that's not enough. The cyclin-dependent kinase 2 right here can also directly phosphorylate and change the conformation of the retinoblastoma protein right down here, so it could push the cell cycle forward. So this cyclin-dependent kinase 2 has two jobs, has two roles that are very important. One is to knock out P27, which is a tumor suppressant protein, which this tumor suppressant protein, if it's not knocked out, it'll continue to bind to cyclin-dependent kinase 4, and cyclin D can't bind to it. And if cyclin D can't bind to it, then it can't phosphorylate the retinoblastoma protein, and it can't push the cell cycle forward. So it needs that push right there, that bump right there, push it through. And so this cyclin-dependent kinase 2 right here knocks this P27 out. So it makes this more available, the cyclin-dependent kinase 4 and cyclin D more available. Not only does it do that, the cyclin-dependent kinase 2 has dual functions. It can go and directly phosphorylate the retinoblastoma protein. So this one and this one can both go and directly phosphorylate the retinoblastoma protein, and that'll change in conformation and push the cell cycle forward. But it has that separate role here of knocking out this tumor suppressant protein, P27. So you get a knockout, and then these two here, when this spikes, can go to phosphorylate and change conformation in the retinoblastoma protein and push the cell cycle forward by releasing the E2F and its binding domain transcription factor. So that is what's going to push the G1 into S phase, or synthesis phase. Now, I said in G1 phase, you have these pre-replication complexes at the origins of replication, where DNA polymerase will bind to. But they're not ready yet in G1 phase. They were just made in G1 phase. And there's multiple ones. And the reason that there's multiple origins of replication is because if you only had one, DNA replication would take forever. So this has multiple ones, but they're not ready yet. So now over here, you have in the S phase, you have cyclin A, or A cyclin, that binds to cyclin-dependent kinase 2. Now you're going to say, well, that name sounds familiar, and that's because it's the same one as here. This is cyclin-dependent kinase 2, which binded to E cyclin in G1 phase, but in S phase, cyclin-dependent kinase 2 binds to A cyclin. So just the binding, this different cyclin binds to it in the S phase. And what this is going to do is this, and I'll show this in more detail in a later video, but right now I'm just going to show you kind of what it does. It just goes to the DNA origins of replication, and it fires them. Boom. So the origins of replication in S phase, because of this enzyme right here, are now ready for DNA polymerase to come in and start replicating the DNA off the template strand. Another thing that I wanted to, there are other cyclin-dependent kinases that go into G2 phase, and G2 phase is where it's making the preparatory proteins for M phase. But I'm going over so much right here, right now, and I really want to touch on something else that's important in this portion right here. So over here we have something called a SMAD complex right here. So the SMAD complex is this R-SMAD comes up to this receptor, and it gets phosphorylated. The transforming growth factor beta type 2 binding binding domain intracellularly, and it gets, there's a lot of stuff right here. It goes up there, and it's R-SMAD, which the R just stands for receptor, and there's not an autophosphorylation that occurs there. It's just one phosphorylates the other, and then it draws up this R-SMAD, and the R-SMAD is either SMAD2 or SMAD3. SMAD2 or SMAD3. And once it gets phosphorylated, it drops down into the cytoplasm, and it changes conformation, and it will bind to SMAD4. So you have a complex of SMAD2 or 3 binding to SMAD4 in the cytoplasm of the cell. And it's phosphorylated right here, and that'll drop down. That's a transcription factor, and that'll go down to its promoter region, and that'll start producing tumor suppressant proteins of P21 and P15. And remember, the little p just stands for tumor suppressant protein. So now this complex right here, and the reason I like this pathway is kind of like anti the game. Like all these other intercellular pathways are for cellular growth and cellular division, and this one's like anti the game. It's like this one's making tumor suppressant proteins. So this one is a very this pathway could actually stop this cell cycle at any point during the cell cycle. It could stop the cell cycle. So it goes down there to its promoter region, and this SMAD complex goes down to its promoter region, and these P21 and P15 start getting transcribed and translated. And the P21 can go over here and bind to, again, cyclin-dependent kinase 4, cyclin-dependent kinase 2, cyclin-dependent kinase 2 here, down in S phase. Then it can also bind to cyclin-dependent kinase 1. So it could virtually stop the cell cycle at any point. And that's from the SMAD complex right there, is that it's these two tumor suppressant proteins can start right here in G1 phase and bind to cyclin-dependent kinase 4 and not allow cyclin D to bind to it, so that it can't phosphorylate and change conformation of the retinoblastoma protein. Also P15 can do the same thing. It can bind to the cyclin-dependent kinase 4, so that the D-cyclin can't bind to it. And these two can also bind to cyclin-dependent kinase 2, so it can keep it E-cyclin from binding to it. So there isn't that spike at the checkpoint right there. So it could stop the cell cycle right there. It could also stop it right here. P21 could stop cyclin dependent kinase 2. So cyclin A can't bind to it. So the origins of replication don't fire, and DNA polymerase doesn't bind to it and start replication. So it could stop the cell cycle right there. And then so on and so forth with the other cyclin-dependent kinases that are going through G2 phase and N phase. So virtually, the transforming growth factor beta pathway can virtually stop this cell cycle at any point, which is a crazy idea if you think about it. So that is it for right now, and I'm going to return to this and kind of try to start keeping things consistent, and that's it. Rich, CNA, see you later.